Hello. So today's lesson is about solving non-exact differential equation. So let us first define what is non-exact differential equation. Given that you have the first order differential equation of the form m function m of xy dx plus the n function n of xy dx equals 0, and this given is non-exact differential equation if the partial derivative of m with respect to y is not equal to the partial derivative of n function with respect to x. And in that case, an integrating factor is sought, or it is necessary, okay, to use. So what is this integrating factor? So this factor should be multiplied to the non-exact differential equation to make it an exact. And this integrating factor is determined subject to the following conditions. So first one, we have integrating factor is a function of x only. So we have this following condition: if 1 over n multiplied by the quantity partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal to the u of x, and that is the u of x is it is an expression which depends only in x alone. Okay, in other words, that u of x is a function and you can only see x variable on it. Then the integral factor will be e raised to the integral of u of x dx. Next, so another integrating factor. So we have integrating factor is a function of y only. So we have this following condition here: if 1 over m times the quantity of the partial derivative of m with respect to y minus the partial derivative of n with respect to x is equal to u of y. Okay, and that u of y is an expression depends only in y alone. Okay, meaning it is an expression where you can only see y variables. Okay, then the integrating factor will be e raised to negative integral of u of y dy. Okay, so these two integrating factors, the function of x only and function of y only, are commonly called the single variable integrating factors. And if this single variable integrating factors doesn't exist, so we have this special condition or special cases that we need to do. Okay, so in case of our differential equation is homogeneous, okay, the integrating factor of it will be 1 over x times the m function plus y times the n function. Okay, use this to make your DE, your homogeneous DE, exact. Okay, so let's have an example here. Okay, so we have x to the cube plus x cubed plus y squared quantity dx plus x squared minus 2xy quantity dy equals 0. So let's identify first the m and n function. So for m function, we have x cubed plus y squared. N function, we have x squared minus 2xy. So to determine the exactness, we need to get the partial derivative of each function, m and n. So partial derivative of m with respect to y, we have 2y, and then partial derivative of n function with respect to x is 2x minus 2. And since they are not equal, therefore, we have a non-exact differential equation. And we need to use, or we need to solve for the integrating factor, so that if we multiply it with our dE, this integrating factor, okay, we multiply it in our given differential equation, we can make it exact equation. Okay, so let us first solve for the integrating factor. So let's use this formula. Okay, and if it doesn't work, so let's try the second formula, which is u of y. Okay, so in this case we use u of x. Okay, and the formula here is 1 over n times the quantity partial derivative of m with respect to y minus the partial derivative of x with the partial derivative of n with respect to x rather. Okay, and that is 1 over x squared minus 2xy. Okay, that is the n function multiplied by the m, the partial derivative of m with respect to y, which is 2y, minus the partial derivative of n with respect to x, which is 2x minus 2y. Further simplify and you will get, okay, this one, you will get negative 2 over x, and this will be our u of x. And as you can see here, this expression, negative 2 over x, you can only see x variable, and this means that it is a function of x only. And now we can use this to get the integrating factor. And the formula here will be the integrating factor equals e raised to the integral of u of x dx. Just simply substitute the value of u of x here. So we have e raised to the integral of negative 2 over x dx. Integrate, okay, so we have e raised to negative 2 ln of x, and then apply the properties, okay, the property of logarithmic and also the exponential. So negative 2, this negative 2 ln of x is similar to ln of x squared, right? And since we have e here as base, so the answer here will be x raised to negative 2. Okay, and this will be our integrating factor, and this factor will be multiplied in our given so that we can make it exact. Okay, this is our original dE, right? And then multiplying by x raised to negative 2 in our m function and n function, so this will give us x plus x raised to negative 3 y squared quantity dx plus 1 minus 2 x raised to negative 1 y quantity dy equals 0. So this will be our new m and n function. So in this case, let's use small letter to indicate that this is a new function. Okay, new function in an exact equation, okay, differential equation. And since it is now exact differential equation, so let's just apply the method of solving an exact differential equation. So this will be the formula, okay, the integral of m dx, okay, and just add this phi of y, plus phi of y, and we will get here answer, which is x squared over 2 minus x raised to negative 1 y squared plus this phi of y. Next, get the partial derivative of this result, okay, this answer. So that will be, so we have this final answer, which is negative 2 x raised to negative 1 y plus phi prime of y. Okay. Then once we have that answer, we need to equate it in our n function, which is our n function is 1 minus 2 x raised to negative 1 y. Okay. So here's it. Just solve for phi prime of y and the answer will be 1. Okay. And then integrate it. So the answer will be phi of y equals y plus c. This is our constant, okay, that we will substitute in our final answer. So to get the solution, okay, mu of xy, okay. So we have here the integral of m function dx, which is x squared over 2 minus x raised to negative 1 y squared plus our phi of y here, which is y plus c. And let's just equate it to c. The final answer will be, we will arrive at this answer, which is c equals x squared over 2 minus x raised to negative 1 y squared plus y. Then further simplify, so we have c equals x squared minus 2y squared over x plus 2y. So that's it. So that's how you apply the non-exact, particularly the integrating factor in our non-exact differential equation, so that we can make it exact equation and solve for the solutions of it. So thank you, and that's all.